Hi everyone! In today's video we are going to continue talking about real numbers. This time we're going to be working with radicals a lot though, simplifying radical expressions. Today you're going to learn to simplify square root expressions using the product property. We're going to evaluate square root expressions by performing operations, and we are also going to be rationalizing the denominator to simplify square root expressions. So first we need to go over some vocabulary. When you have a radical, the type of radical that you're taking is called the index. It's where this n is here. So when we usually look at square roots, that 2 is implied, that you're looking for pairs of factors that will come out and simplify. You can also have an index of any number. So it could be a cube root, it could be a fourth root, anything else. You get the idea. The inside piece, this x to the m power, that's called the radicand. It's just a fancy way of saying the thing that's in the radical. And there's this really great rule that's going to help us get rid of those fractions from the previous lesson. When you have a base with a fractional exponent, like we do here, you can convert that into a radical, where the numerator of the fraction becomes the power of the radicand, and the denominator of the fractional exponent becomes the index of the radical. So we're going to simplify our real numbers using our exponent rules, and then once we've simplified all the way, we can convert them to radicals and finish simplifying them. So first let's just do a little bit of practice going back and forth between these two notation formats. You can see that I've given you the exponential notation for several different terms here. So let's change them to radical notation. The base is going to be the base of the radicand, so I'm going to draw my radical and put the base of 3 inside. The numerator is going to become the power. So that is the exponent, or the power, for that radicand. And the denominator is going to become the type of root that you're taking. It's the index. So this is a 2, or square root. So the square root of 3 is 3 to the 1/2 power, written in radical notation. This idea of power over root will be a nice way to help you remember which number goes in which place, the two parts of the fractions in the radical. The number on the top is the power of the radicand, and the number on the bottom, the denominator, is the root, the type of root you're taking, square root, cube root, fourth root. Okay, so let's do another one. I'm going to draw my radical sign. The base becomes the radicand of 7. The power is the numerator, and the index is that the denominator, the root, so that is a cube root of 7 to the 1st power, or a cube root of 7. This next one, the base is 5. The power is a 1, and the denominator becomes my type of radical, so that's a 4th root of 5. All right, now this next one is a little bit different. I still have my radical, I still have my base of 11, but this time my power is a 2 because of that numerator, and this is a cube root. And then for this last one, I have a base of 2, so that becomes my radicand with a power of 3, and it is a 4th root because of that denominator. So power over root. The top number is the power, the bottom number is the type of root. So let's just do some basic review of something that you should have learned in Algebra 1 quite well, our square roots. It is essential that you have these square roots memorized. So if you don't know all of these square roots, make some flashcards and get going on them. When we talk about simplifying square roots, we are going to be assuming the positive version, and this is called the principal square root. So if you see in your directions anywhere anything about a principal square root, it just means you're assuming positives here. Oh, sorry about that. Okay, so the square root of 4, 4 is 2 times 2, so that's the square root of 2. The square root of 9 is 3, because 3 times 3 is 9. The The square root of 16 is 4 because 4 times 4 is 16. Square root of 25 is 5 because 5 times 5 is 25. All right, and I'm going to speed up here. Square root of 36 is 6. Square root of 49 is 7. Square root of 64 is 8. Square root of 81 is 9. Square root of 100 is 10. Square root of 121 is 11. Square root of 144 is 12. And then if you don't know these last three, these might be your ones to memorize if you knew all the others. The square root of 169 is 13. The square root of 196 is 14. And the square root of 225 is 15. So I am going to ask that you memorize all the way up to the square root of 225. A fun little thing to notice. Notice that in the square root of 169, that 6 and that 9 trade places to be 96 for the 14. So the smaller number is with the 13 and the bigger number is with the 14. Maybe that will help you memorize them a little bit more quickly. Just a fun little coincidence. Okay, so let's look at simplifying square roots, because once we get rid of the fractional exponent by changing it to radical notation, we'll have to deal with that radical. Okay, so I'm going to show you the alternative method first because I think this is probably what many of you already do, and then I'm going to show you a better method that will help you as we go through the rest of simplifying radicals over the course of the school year. So many of you learn to simplify radicals by making a factor tree. So if you had to simplify the square root of 72, you might immediately think, well, 72 is 8 times 9, and 8 is 4 times 2, and 4 is 2 times 2, and 9 is 3 times 3. That then means that you have 2 times 2 times 2 times 3 times 3. And because this is a square root, we're looking for pairs. So that's a pair of 2's that come outside of the radical. There's a pair of 3's that come outside of the radical. And this 2 doesn't have a partner. Remember, this is a square root, so I'm looking for a pair. He doesn't have a buddy to come out with, so he stays inside. And then I just multiply 2 times 3 and get 6 square roots of 2 for my final answer. What I have found, as these are going to get more complicated because the square root of 72 is a pretty easy one for right now, is that a lot of times students miss like maybe this 2 here and then won't include it, and so they'd only get like 6 for your final answer. And I want to be sure you don't make those kinds of mistakes, especially as things get more complicated. So because of that, I want to show you another method that's going to be much more helpful to you in Algebra 2 this year. And that method is to take whatever your radicand is, and to starting with 1, list out the possible factors that multiply together to get that radicand. And you do want to go in order here. So I'm going to start with 1 times whatever. Then I'm going to try 2, 3, 4, and so on. So 72 divided by 2 is 36. So that works. 72 divided by 3 is going to give me a decimal, so I'm not going to write it down. But then 72 divided by 4 is 18. 72 isn't divisible by 5. It gives you a decimal. 72 divided by 6 is 12. 72 divided by 7 is going to give you a decimal, but 72 divided by 8 is 9. You can use a calculator to help you with these if the numbers are big and you're on a calculator portion. But coming up with this list of numbers is really important because remember those square roots we just went over? Here's where this is going to make it crazy easy. I am going to look, starting on the side with the bigger numbers, for a perfect number for one of my square roots. And I see 36 here. Because that's my biggest square root number, notice you have 4 and you have 9, but 36 is larger, so I'm not going to use these smaller ones. I can rewrite square root of 72 as square root of 36 times 2. So I'm using that multiplication there that I just came up with. And the square root of 36 is easy. We know that's just 6. Square root of 2 doesn't simplify at all, so it stays inside. And then I have my answer, the 6 square roots of 2, and I'm done. So you can draw the factor tree. You can find all of your pairs if it's a square root. You have to be careful not to miss anything, and then you can pull out whatever you have. You'll get the same answer, but by taking a moment to make this list looking for your biggest perfect number, you're going to save yourself a lot of work and a lot of potential missed mistakes. Okay, so let's do this a couple of times. This next one, I have the square root of 27. So I'm going to write 27, and then I'm going to start thinking about what numbers multiply together to get 27. I'm always going to start with 1 times that value of whatever it is. So this one's 27. 27 isn't even, so 2 does not go into 27 nicely. 3, however, is 3 times 9. And I'm actually going to stop right there because over in my right-hand column, I have a perfect number. And as soon as I get in my right-hand column that has my big numbers in it, not my 1, 2, 3, 4, 5, that's going to be my biggest one. So I'm going to rewrite this as the square root of 9 times 3 using that pair of factors. And then the square root of 9 is 3, and that square root with the 3 stays inside. So that's my final answer. All right, let's add one more step to this. This one is written in exponential notation. I need to change it to be radical notation because it doesn't simplify anymore or any further without it. So I'm going to draw my radical. I'm going to put my radicand, my base, inside. The power is 1, and the type of radical that we're working with is a 2, so that index is 2. It's a square root. I'm going to write 32 over here on the side and list out my factors. I have 1 times 32. I have 2 times 16, and I'm going to stop right there because that's a big perfect number, and it's in that right-hand column. It's in my big numbers column. So I am going to write this as 16 times 2, all inside of my square root. The square root of 16 is 4, and that square root of 2 doesn't simplify, so that's it. Okay, so let's talk about some operations now. We are going to have to add, subtract, multiply, and divide square roots. So in order to add or subtract, you must have the same index and radicand, meaning the number inside of the square root, in this case, has to be the same, and they both have to have the same type of index out here, meaning they have to both be like square roots. One can't be a square root and one be a third root or something like that. They've got to match perfectly. So when they match perfectly for addition and subtraction problems, these are going to be, the radicals are going to act just like variables. So if I gave you the problem 1x plus 4x, well, you would say, well, that's easy, Miss Yee. 1x plus 4x is just 5x because you add together the coefficients and not the variables. The same thing is going to happen with our radicals here because our radicals match. They're both the square root of 3. You're going to add together the coefficients out front. So this is 1 square root of 3 plus 4 square roots of 3. That's 5 square roots of 3, and you're done because that one doesn't simplify any further. If you multiply, you only need to have the same index. That means they have to be the same type of radical, but the number inside does not matter. Now, to keep my numbers small, especially if I have to do this without a calculator, I am always going to simplify each radical individually first. So let's just simplify the square root of 12 before we do anything else. I'm going to make my list of factors. 1 times 12, 2 times 6, 3 times 4. I'm stopping there because I have a 4, and that's a radical or a perfect square that's in my big numbers column. So I'm going to rewrite this as 2 square roots of 4 times 2, and then I'm going to write this 5 square roots of 18 over here. The square root of 4 is 2, so that's 2 times 2, and this other 2 stays inside. I'm going to leave my 5 square roots of 18 the same for a moment. We'll deal with him in a second. So I have 2 times 2, that's 4 square roots of 2 times 5 square roots of 18. All right, so now let's do the same thing with the 18. I'm going to list out all the possible options I have. So that's 1 times 18, 2 times 9, and I'm stopping there because I have a 9, which is a perfect number. So I've got 4 square roots of 2 times 5 square roots of 9 times 2. All right, and then I need to simplify that radical, so I'm going to leave my 4 square roots of 2. Square root of 9 is 3, so that's 5 times 3 square roots of 2. And then I need to multiply these two together the same way I multiplied those two together up there. So 4 square roots of 2 times 15 square roots of 2. I have the same index, so now I'm going to multiply. When I multiply, I'm going to multiply the... did I mess up? I did mess up. Look what I did. This should have been 4 times 3, shouldn't it? All right, so I'm just really quickly going to change down these because 4 times 3 is 12, not 4 times 2. Okay, that was more of what I was expecting. Okay, so now the multiplication says that you multiply together the coefficients. So I'm going to multiply together 4 times 15, which is 60, and I am also going to multiply together the radicals. So inside of my radical now, I'm going to have 3 times 2. Now 3 times 2, there aren't any pairs there to come out of the square root, so my final answer is just 60 square roots of 6, multiplying those two together to get to my final piece. Okay, so now the last big thing that we need to talk about is division. There are going to be super quick and easy division problems, and there are going to be ones where we have to do a little bit more work. So let's talk about the easy ones first. All you need to do division is to have the same index in two radicals. So if you look at this first one, the square root of 20 divided by the square root of 5. If the two radicals are both the same type of radicals, they're both square roots in this case, then I can write these as the square root of 20 divided by 5, all inside of one radical. Now the reason that's nice is because 20 is divisible by 5. 20 divided by 5 is 4. And then in this one, that happens to be a perfect number. The square root of 4 is just 2, so I'm done. If you can use this division rule, it is going to definitely be the easiest way to do division problems. The only time you can use it, though, is when the index is the same, and you have to be able to divide the numerator by the denominator and get a nice factor, like 4. There are going to be times where this isn't possible, though, and we're using the strategy called rationalizing the denominator when we're not able to easily divide like we did in that previous one. You also are going to need to simplify any fractions that you have if there's a radical in the denominator. So the way that we're going to do that is that we are going to get the radical out of the denominator. So for this first one, I have the square root of 3. Now if I had the square root of 3 times 3, that would be the square root of 9, right? And that doesn't have any radicals in that simplified answer. So what I really want is another square root of 3 in the bottom. I want this second one that I don't have here. So I'm going to write my fraction, and the rationalizing part is when we multiply by the same thing on top and bottom to make this radical simplify. So I need a pair of 3's. I only have one. So I'm going to multiply on top and bottom by the square root of 3. Because what this does, if I just look at the bottom for a second, is my coefficients are 4 times 1, that's just 4. And then when I multiply my radicals together, like we just learned, 3 times 3, 3 times 3 is 9. And the square root of 9 is just 3. So by doing that, in my denominator, it gets rid of that radical, which is what I want. Now I have to also do this in the top. I need to do 5 times the same thing that I multiplied on the bottom. So I have 5 times the square root of 3. Now I can't multiply together the 5 and the 3 because one's inside of a radical and one's outside of a radical. So I'm just going to carry that guy through the rest of the problem. And my last step is just to multiply that 4 times 3. So I have 5 square roots of 3 divided by 12. That fraction doesn't simplify anymore, so that's my final answer. Okay, so, and there's one more level of difficulty to this. So if it's easy, divisible fraction, we can put them all together and just divide like we did in this first one. If I can't do that easy division, or maybe I don't have a radical in the top. I can multiply on top and bottom by the piece of the radical that's missing to get it to be a perfect number. But notice this was 4 times that square root of 3. In this last one, we have 2 terms. We have 3 minus the square root of 7. So we can't just multiply by the square root of 7 in top and bottom, because this guy is all stuck together. And if I were to distribute the square root of 7 over the square root of 7, I'd still wind up with a radical in the bottom. So what I'm going to do instead is use what's called the conjugate. That is just a fancy word that means it's exactly the same thing, but with a opposite sign in between the integer and the rational number. Or, I'm sorry, the real number. So because this denominator is 3 minus the square root of 7, I'm going to multiply on top and bottom by the conjugate, 3 plus the square root of 7. Notice that the only thing that I changed was that subtraction sign became an addition sign. So here's what happens. I'm going to have to do some distributing up top. So I have 2 times 3 plus the square root of 7. I'm going to have to do that distributing in my next step. And in my denominator, I have these 2 factors that I'm going to have to multiply together. So I'm going to have to use the distribution property to do some distributing there, or foiling together, if you think about it that way. So let's do all of this distribution. On my numerator, I have 2 times 3 and 2 times the square root of 7. In my denominator, I'm first going to distribute 3 times 3 is 9, and then 3 times the square root of 7 is positive 3 square roots of 7. When I do my inner, I've got 3 times negative square root of 7, so that's negative 3 square roots of 7. And then my last is negative times positive, and then 7 times 7 is 49. So that's inside of that radical. Okay, I know this looks a lot worse, but look at these middle terms down here. Do you see these guys? They equal 0. 3 square roots of 7 minus 3 square roots of 7 is 0 square roots of 7. So I have that 6 plus 2 square roots of 7 on the top, but down in the bottom, I only have that 9 minus the square root of 7. So, or I'm sorry, the square root of 49. So I have 9 minus the square root of 49 is 7. So that leaves me with 6 plus 2 square roots of 7 over 2. I no longer have a radical down in the denominator. Now, this one is not quite done yet. We are almost there, but we have some fraction reducing to do. If I take this common denominator of 2 and I put it underneath each term, okay, so I split it up to be 2 fractions instead of 1 common denominator. 6 divided by 2 is 3. And 2 divided by 2, those divide out and leave me just with the square root of 7. So that is my final answer simplified all the way. Sometimes that division won't happen and you'll be done on this step, but you should always break it into 2 fractions under your denominator just to check and make sure nothing divides out. Okay, so in this video you learned how to simplify square root expressions using the product property, and then we evaluated square root expressions using operations, and we rationalized denominators to simplify some as well. Go ahead and try the practice problems in the Now You Try.